Okay. Thank you very much for coming, everybody. We have a small audience here, but we have a bigger one in Piña. We have 4 professors actually over there. So it's going to be a good talk. So this time we have Juan Perez. So thank you very much for coming. Juan is a professor at the Universidad de los Andes, and he giving his talk on credit scoring using support vector machines. Thank you very much.
Thanks for the invitation. This talk, I'm going to talk about credit scoring using super vector machines approach. This approach is, we are going to modify the classical super vector machine approach by introducing some budget constraint in order to consider some specific issues for a financial institution in Chile, Chilena Consolidada. Okay. Financial institution in Chile. Okay. This research is with Sebastián Maldonado and Cristian Bravo. Sebastián Maldonado at the University of Los Andes and Cristian Bravo at the University of Southampton. Here is the agenda. We are going to talk a little about the context of this problem at the beginning. And not related to the mathematical model at the beginning, but the problem that the financial institution is facing. And the second term, we are going through the models. There are 2 proposals, 2 variants of the models. The data that we have, we are going to show in the next stage. And finally, some conclusions and some results. We are now working on that, and then is some preliminary results. Okay, before I have to explain, before talk about feature selection, I have to talk you about the problem. The problem is you have it's a Chilean financial institution. This institution have to decide whether or not they are going to give a credit to individual. This individual can be a person or a small company and you have to decide to grant the credit or not, considering the characteristics of each one of the individuals. Okay, what you have as a material is your analysts, your personnel. You have some information, historical information of your actual customers, and you also have some surveys that you buy, some reports from specialized firms that do some research about customers. Okay, then you have all this information, and with this information you have to decide. You have to wonder how you are going to decide if you are going to give the credit or not. Another important issue is that you have a budget to do that. You don't want to pay a lot of money in this process of credit scoring. Okay, this is quite expensive. I'm going to break that to show the amount of money they spent in this kind of process. Okay, the first part then is our approach is, first we are going to look this problem as a super vector machine classification approach, classical approach. Then we are going to perform a feature selection methodology in order to make the model easier to understand, to the methodologies work faster. And I'm going to go through this with this slide, and we propose 2 models, 2 modifications of the super vector machine classical approach to do this mixed approach in between using feature selection and super vector machine. What is feature selection? Okay, let's consider that you have some historical information about customers. The customer, some of them pay the credit, some of them don't pay. This is the most important attribute or feature of that individual, and you have to decide according other characteristics if you are going to give her or him or a company or not the credit. With this information, you have to realize, you have to see that some of the information is not really important. Maybe it's redundant, maybe it's irrelevant. Sometimes the databases are huge, and then you have to reduce the information that you are going to use in your model. Of course, why is this important? Let's make some brief points about why it's important to have a low-dimensional representation of the customers. It improves the model generalization because you are using less information. But the most important, from my point of view, from the real world problem point of view, that it improves the data understanding. Okay, if you show to the decision maker a model that is using few information, you can explain it better. Okay, and as we can see, then it is also possible to reduce the data collection cost, because right now in this context, this process of credit scoring is expensive. You have to buy information, you have to make some analysis, and you use the time of your personnel, then it is expensive, and you reduce cost. Okay, of course, it requires less computational effort since the databases are smaller. Then in this context, this is what feature selection do. But where are we going to perform feature selection? In the context of, let's go to the next slide. I'm going to back next. In the context of one of the classical ways to separate two types of customer, which is the super vector matching approach. The super vector matching approach is an approach in which you have some class of customers. This class of customers is in gray dot. This class of customers in white dot. This type of customer will pay the credit. These don't pay the credit, and you are looking for an hyperplane which separates for both classes. Okay, what you have is the data. This is what you have. You have this data. You have the label. The label is gray or white, and the label is a parameter y. Is a parameter y that is +1 or -1, and you have to find this hyperplane to separate both classes. Okay, this is a classical approach. This classical approach can be a model. We can see the model. This is the classical model of Babnik. In this model, we minimize the weights of each of the attributes. Not the label. This is the label. This parameter. This is a parameter. X is a parameter too. Ya is a parameter +1 or -1. This parameter tells you whether if it's in the right side in the left side of the hyperplane. Here is the hyperplane. These are the characteristics or features or attributes of each one of the individuals in the population. These are the weights. These are the weights of each one of the features. This is parameter B or for any hyperplane. And here we have a term to allow the possibility to have some errors. Okay, you can have errors, and the classical, if both classes are completely separable, you can use this model, but we add this term to allow some errors. Okay. We don't know the exact value for constant C, and we are going to. This is all of the parameters that we don't know. We are going to calculate it by heuristics. It is called hyperparameter estimation. There are several techniques to do that. Okay, I'm going to explain that. The
right-hand side of the constraint should be greater or equal to 0 normally, and then relax to -ci.
Again, please. Again.
The one, which is
okay.
there, shouldn't it be 0?
Okay. Okay, yes. This in this case, the hyperplane is equal to 0. This is the supporting vector for the class right here is 1, and the supporting vector is, in the other hand, is -1. Okay? Then you can separate both classes, and this point, of course, is 0. Okay? This hyperplane. Yes.
Completely separate, right?
In the case.
The two
Okay, there are ways to separate, or you can allow some errors. For example, if you have a gray dot over here and you allow a error, another way to do that is to apply some kernel functions that you, instead of having of representing this data in this space, you apply a function to separate them. Okay, and you work with data separate. It is possible to do. It is possible to do, but we are using the approach using errors. Okay, maybe you can mix it also. Okay, it is possible to do that. It is called the kernel trick. The kernel trick. Okay. Well, that's. Well, let's take a look of this model. This model is quadratic, is convex, is nonlinear. Okay, it's easier to solve. It's easy to solve because it's convex, but it is nonlinear. It's a nonlinear model. You can turn it in a linear one using the first order condition, since it's a linear complementary problem. The first order condition is a linear equation system, then the problem is linear. But as you can see here, this is a non-linear problem. But you can cast maybe in some kind of linear problem if we use the lasso penalty here. But again, it's non-linear because you have here the sum of the absolute value of W. Then it's non-linear again. But you can convert this, you can cast this problem into a linear one by use a classical transformation. You can cast the variable Wj in between Vj and minus Vj, and you minimize Vj instead of minimizing, you tackle Vj, you tackle Yj by minimizing Vj, the sum of Vj. Okay? This model do the same work as the previous one, but it's linear. Okay? This is good because it allows us to propose to do our proposal. Okay. Another approach to do that is not is a proposal by Zhou in 2002. And this model, instead of tackling the variable Wj, you cast the variable in between -1 and 1, but you maximize the margin. Okay, you maximize the margin instead of do that. This one goes to the objective function, and you maximize it. Okay, you maximize it. This again is linear. Okay. As I have already told, we are looking for an approach that allows us to make feature selection. But in the previous model, we are not doing any feature selection. We are using all the features that we have available, and we use it to construct our hyperplane. But let's take a look to the first formulation, in which we tackle the value of Wj. We again tackle the value of Wj by using this variable Vj bar. And this variable Vj bar is going to be controlled, some kind of control, via using binary variables that activate using the big M constraint. If you use it, then it's going to be activated. Then the variable Wj is going to be 0 if you don't use the features, and it's going to be minimized in his absolute value if you use it. This is some kind of reducing, not this of kind, is reducing the dimension of the hyperplane. What you are doing is reducing the dimension of the hyperplane. Okay?
But the lasso will also try to do that automatically, right?
But in I agree with you, but it doesn't do the work because in sometimes it uses all of the attributes, all of the features using a small weights for all of the attributes. It tries to minimize, but they are not zero. They are a small value, but they are using all of the attributes. Okay, this is a problem. This is a problem because we are looking not to use all the features. Okay, and in this approach allow us to do that, and we are also constraining the total budget that we are spending in the process of credit scoring. We are representing this via a variable cost. If you use or not this feature, and the total cost of the features cannot be greater to the budget. Okay, and this model can be also this approach can be also used to extend the proposal of SOLVE of 2002, the one that maximized the margin, the same approach. And these two models we have published in a paper 2 years ago, again with Sebastian and Christian Bravo. Okay, we have already presented that in not exactly like that, but without the M constraint and using some extra parameters, extra hyperparameters here, lower and upper bound. But it's quite similar to the proposals from 2 years ago. Okay, but in practice, what happened with the original research? What happened with this budget constraint? In practice, you cannot think in just variable cost because the financial institution faces a process of credit scoring in which you have some task to perform. This task involves a sequential execution, and this task implies that you have to spend a fixed cost, money in a fixed cost, and also a variable cost. And you have then variables of families of features. In each one of these families of features has a fixed cost and also a variable cost. And in this context, the first step is to make a credit evaluation. Is pretty easy. You receive the application from the customer, and you have some very basic information. If you see that the customer has potential, you decide whether or not if perform a more detailed interview, and you gather more information, but you spend more money because you are using your analyst time, etc. Then you can perform some financial analysis, preliminary, some basic evaluation that the company performs. There are other information that you can buy. For example, DICOM o la Superintendencia de Bancos y Instituciones Financieras. You have to buy. This is very expensive. You have to buy it. And finally, you can perform some new financial analysis. Fixed cost plus variable cost in all of the cases, precedence for all of these tasks, and then we can represent the basic version of the budget constraint, that variable cost with a budget, now with a variable cost, but with an activation cost for the fixed cost. Okay, an activation variable for the fixed cost. This total cost the maximum value is the budget. You activate the fixed cost if you are using at least one of the features inside the family, and of course there are some precedence constraints. Then the constraint, the basic constraint. This constraint, the basic constraint, is replaced by these three family of constraints. Okay? See? Yes.
So to run the program, I need to know all the values, right?
See,
the program
yes.
decides which attributes. We need to know all of them, right?
Mm-hmm.
But then, so I must have already paid to have those values, right? The fact that I choose to
I understand. The approach is that you have all the information about historical data and you are analyzing what we are going to do for a possible or a future incoming customer. Then if you have all the information of the past, you evaluate this in this way from the model when you are constructing your hyperplane. But in the future, when you are going to evaluate a new customer, then you decide. Okay, this is for the construction of the hyperplane. Okay.
So the third value is precedence constraint. These are for all pairs. No,
No, for all pairs. For
some pairs.
For some pairs. I don't remember exactly.
This is just sequential.
In this case, it's just sequential, but in practice, the process was very big. Then we couldn't represent it with the data we had, but because we didn't have all the information. But in this case, the sequential is easy. It's a diagonal matrix. Okay, it's an identity. Okay. Then what we have two models, we have two proposals. These two proposals, we are going to evaluate this proposal with some data. I'm going to talk about the data in the next slides. But what we are going to do with general data, we will perform a 10-fold cross-validation procedure. It's a classic procedure in which you have information, you have all your database, you take a small part of the database and left it apart, and you construct your hyperplane with some part of the information. You construct your hyperplane, and you randomly select this same project, this same procedure. You perform it by choosing randomly this small set of features, and you are letting apart 10 times with 10% of the information about, and you construct 10 hyperplanes, and finally you use the average, the average hyperplane in your result. Of course, because you have a lot of information, you have to do that. Okay, since we don't have, we have the information about the budget, but we think that it's important to show to the decision maker what is the effect of introducing a budget into this process. Then we perform a sensitivity analysis over parameter B. Okay, our main performance metric is the classification of the model, but the classification is corrected. The name of this corrected metric is the area under the curve, that means that there are some cases, there are some databases that are not balanced in terms of classes. Of course, there are classes that are smaller than the big one, and in these cases you have to correct the accuracy. Since, for example, if your model class is 1% of the population, then your accuracy is going to be always 99%. Okay, whatever you do, then you have to correct this indicator, and we use this indicator to do that. What we had as information, we had two databases. One of them is the historical information of the financial institution. That historical information has 6,000 registered about, and a new customer database containing 25% of the historical database coming from the company. This database of new customers is some kind of survey, a report that they pay for that. Okay, this database, the new one, the database of new customer, is balanced. Okay, the paying class and the not paying class are quite the same size, and the database of the historical database of returning customers is not balanced. Okay, we have to deal with that. If the same methodology is performed, yes.
How many features do you have in every range? 5,000 customers?
We have maximum, I don't remember exactly, but it was 100. Less than 100, more than 80. Huh? I don't remember exactly, but this is the. It's important that because in some cases, for example, you have a lot of features, and the model have to be solved with a dual approach. For example, the cases when you are trying to identify if you have cancer or not, you're looking at the genome, and there are a lot of features, and then instead of using X this way, you have to transpose and use a dual approach. But in this case, this is not the case. Okay, this is not the case. Here is the how it's really easy how we calculate the parameter C, the hyperparameter C. For both models, the version of SO of 2002 modified, the modified version of that model, and the lasso penalty the modified lasso penalty approach, we run the tenfold cross-validation procedure using maximum budget, and really not maximum budget, infinite budget, not considering the budget constraint. Okay, this is important for us because we are looking for the C that maximizing the performance of the hyperplane. Okay, the area under the curve, the accuracy. Yes.
So you have a training set, no?
Yes. Yes, I have. I have it. I split the tenfold cross validation procedure is you have all the information. You divide it. This is for some kind of train. You construct your hyperplane, and this is for testing purposes. Okay, you do it 10 times.
Also, the 10 training.
10 training sets, and always random. Okay, 10 training sets. Then your final hyperplane is the average of those.
Using the final thing, then you have a validation set for everything.
Yes. We left apart. Thank you. We left apart. Okay, at the beginning of the project, we do that. Okay, we reduce the original database in, I don't remember, maybe 10%. I don't remember exactly. Okay, that's right. Okay.
500 on each one.
Yes. And this is the tenfold cross validation approach. We calculate C running this procedure, this heuristic. We find to maximize the AUC, and we run again the tenfold cross validation by making sensitivity analysis over the budget. Okay, but we did using the same seed of random. Using the same sets. Okay, we stored the random selection at the beginning of each trial. Okay, and using this approach, we are going now to compare these two methods, the two models, with the performance of other methodology. Which one? The feature plus F plus super vector machine classification. This method does not allow to make feature selection, but you control the number of features they use by not by limiting the cost, but by limiting the number. Is a mixture in order to make comparable to our model. We introduce we limit the number of features that can be selected, but not with a cost criteria. Okay, because if we don't do that, the model use all of the features. They use simply all, and always the cost is the maximum. Okay, in most of the time, to make it a limit, just a limited, and
The feature choose which.
Feature again using the AUC, again using the accuracy corrected, the performance metric. Okay, and what we have, if you use few parameters, few features, then you have a poor performance. But if you use in some point, if you use more parameter, this is the performance. Sorry, this is the performance. The squared and the circles are in yellow are the cost. Here you have a low cost, of course, but in this point you use almost all. You spend all of your money, all of the cost. You use all the money you have, and the number of features grows. Why this happens? Because a lot of features are in practice are represented only by their fixed cost. Okay, some of them, more than 50%, has just their variable costs are 0.
So we have a small number of features, like about 20. The cost is if they have 90 features.
Yes. Some of them, most of them has. We are activating here most of the fixed cost. Then through here you don't have new. All of the cost that you activated has a 0 variable cost. Okay, that's most of them in the using the database coming from the company. Okay.
But I'm not paying the feature for those that I don't select.
But you have to do in most of the cases, because if you use just one of the features inside the family, you have to pay the complete fixed cost. Okay.
You buy a database.
Yeah, that's
Okay.
yes.
Okay. The same pattern you can see using recursive feature elimination plus SVM, and in this case the performance is worse. But again, you are spending money.
I was expecting a monotone AUC. Well, it seems that around 30 drops down.
This is because that you don't. In fact, as you can see, sometimes you can see this here, but sometimes in our trials, because it's an average of hyperplanes, sometimes you have non-natural numbers in maybe 2 and 0.5.
R squared adjusted in regression to have a lower value. The adjusted I squared tries to incorporate the number of features also, right?
No, not really. It is because you have the DJ variable tackling the variable WJ, and this is for the trial 1 to the trial 10. And then in this case, you are using maybe 10. In this case, you are using 11. In this case, you are using 15. And then in mean, you are using maybe some number in the middle. Okay, this is the reason. Okay, this is for the new customer database. This database is balanced. And
another question,
yes.
to interpret the graph, AUC runs from 0 to 100. 100 is perfect. And
Yes. AUC is a percentage. It's a percentage. And it's good. It's a good percentage. Okay. If they run, or if they decide by experience, they are something like flip a coin, 50%. Yeah. Then 20% is 70% is good for them. Okay, the same result, but for the returning customer database. But now it's a little bit confusing. Sorry about that. But I have put the budget here in the x-axis because it is a variable for me. That's the only reason. I change the budget, then I take a look to the number of features I have selected for the lasso penalty modified version of the model, and here is the SO 2002 modified version of the model. Both cases, as you can see, that the performance is good. The number of features is low. Here is a problem. If you gain a small amount or a small accuracy, then you have to spend a lot of more attributes. You have to use more attributes. Okay. This is almost the same behavior here. The same behavior here. The most easiest way to see it.
So the more you spend, the less accuracy.
The less accuracy. It's strange, but let's take a look to the summary. Here is the summary. Let's take a look for the new customer database. In this case, is all of the methodologies are competitive. All of them are in their maximum respective values. They are near to 70%. Okay, then we cannot say this is better. No, since it's random, you can maybe it's really near. Okay, but the number of attributes are different. You use here very few compared to these two classic models. Our proposal are using less attributes. Okay, but the most important part is here. Here you have 60,000 euros, and here you have maybe 10% of that. And this is important. Okay, this is important. I have this is for one trial. In fact, you have to. This is an error. I'm going to take note for that. Not an error, but if you see, we have some kind of. Here is the how many resistors we have. The 10%. This represents this number. This cost represent about the cost of 1 month of analysis. Of credit scoring analysis, okay? About. Then, because it's for new customers, you have, this is for 1 month. Then, in 1 year, this is important, it's near to $1 million if you assume some demand forecast, for example, okay? And this is important for us. This is the first thing you can see, and in the other case, this database is bigger. Then it represents maybe, of course, 4 months, approximately 4 months of evaluations, and again, look at that. Look here, the total cost is 10%. Okay, a little bit more than 10%. But the important part here is that you have the accuracy, corrected accuracy, is similar. Okay, it's the model are competitive. They are behaving pretty well.
What was the budget constraint here? What was for the tables? What was the thing?
The real one. I don't remember exactly the number, but this is not using all of the infinite budget. The budget that the company has, that was they spend more. In fact, they have a budget of $1 million per year to perform the credit scoring, all the credit scoring process. Okay, $1 million per year, including personnel, including furniture, including everything. Okay, that's what the budget.
What is the difference between undersampling and
the undersampled version of the database is that you have here this database is not balanced. Then what we do is this approach. You take this database and you make it smaller, to make it small, the bigger class, and this is called undersampling. This is, of course, you are losing information here. This is not good. The other approach, if you make it smaller, but not that in this way, and you make it bigger. This is undersample and oversample. Again, this is not real, but you are losing less information. Okay, it's quite simple. This is the approach.
What is the difference between the L1 in this VM and LP in this VM?
This one is the version in which we are minimizing the sum of the absolute values of W. When we are tackling and this is the other one is when you are using Wj in between -1 and 1, and then you maximize the margin. Okay? This is the margin approach, and this is the lasso penalty approach.
In the previous case, the cheaper was the LP.
Yeah.
Yes, it switched. Yes.
Yes.
In the previous case, the LP was super slow. But
Yes, we don't know why. we are right now we are working on that. Let me give you some concluding remarks, but also let me give you some information about what we are working on, because it's important for me to have your opinion. But what we did here, we presented two super vector machine based strategies for simultaneous classification. Of course, there are two new models. There's a novel we have already. This paper is under revision right now. We have identified the relevant attributes, okay, in terms of cost. We select fewer attributes. This is a fact, and of course at a considerably lower cost. The other one thing is, let me tell you a little bit about we are working right now. Let's take a look to the model. The classic model is you have to minimize the Euclidean norm of the weight of the attributes. Also, you have here the parameter C for the minimization of errors, and you have here three equations. The hyperplane, the budget, and some big M constraint. Okay, this is our approach. This is what we did. And how we calculate this one? By maximizing the AUC. But we are thinking right now doing this. What if we, instead of doing this, we do this? And we have a discussion here, because if you use this objective function to calculate this lambda, you are looking for the best hyperplane that respect the budget constraint. This is one approach. But the other approach is if you think in maximizing the AUC, thinking in lambda and C. And we don't know which one is better. This approach, the first one, is we are working on that right now. It's really easy. You propose a Lagrangian relaxation. You can propose any subgradient medium to solve it. It's easy to solve. We are working right now to formulate this approach. But we are not clear. We don't have any idea what happened with this one, and we are working on that right now. We think that maybe if we use this approach, we may modify the hyperplane, maybe in a way that is not good for the statistic properties of the classification. But we are working right now on that. Okay.
What is the motivation for doing the relaxation, the Lagrangian relaxation?
The motivation is to have an idea of the effect of the budget constraint on the hyperplane construction in terms of this is some kind of money over money. How much money are you going to spend? Then you can think in terms of performance. That we think that this is important to know the relevance of the budget constraint in terms of the minimization of the maximization of margin of the construction of the hyperplane. Okay, that is we are working right now, and that's all the results we have.
We have a